Okay, I'm going to run through a quick review of kinetics equilibrium. So here we go. So first of all, we talked about things that actually can affect the actual rate of a chemical reaction. In this situation, we talked about concentration, we talked about activation energy, temperature, reaction mechanism, and catalysts. So kinetics, again, is talking about the rate of a chemical reaction. Now, remember, the two key things for a successful reaction are collision geometry, it must be oriented correctly, as well as kinetic energy. So collision geometry or kinetic energy, think of hitting a baseball or a field goal kicker kicking a football. They must have two key things. They must have enough kinetic energy, but you also must hit the ball correctly. Like with a soccer ball or a football, or you're going to shank it, or a golf ball. So again, you want to make sure you once again have enough kinetic energy, and that kinetic energy has to exceed the activation energy, and you must have the correct collision geometry. Now, concentration. Concentration doesn't focus on either kinetic energy or collision geometry. All concentration does is when we increase the concentration of reactants, we're just increasing the number of collisions. And the more collisions we have, the more successful those collisions will be. The nature of the reaction, we're talking about exothermic and endothermic. We'll take a look at them in just a second. And activation energy is the minimum energy necessary to initiate a chemical reaction. So to get over the hill. Temperature. Temperature focuses on kinetic energy. It actually will increase the number of collisions because they're moving faster, but the primary aspect is temperature, increased temperature, we increase the kinetic energy. Reaction mechanism, that just goes after the slowest of our elementary steps. The slowest runner on the relay team, the slowest swimmer on a relay team for swim, that is your rate determining step. And lastly, catalyst. Catalyst lowers the activation energy. So again, collision, what's necessary for a successful collision? You need the correct collision geometry, but you also need enough kinetic energy, and that kinetic energy needs to exceed the actual activation energy. So what do we mean by activation energy? First of all, a couple of things. Activation energy is a positive value. It depends upon the nature of the reaction, whether it is exothermic. Remember, fast is XO and slow is going to be endothermic reaction. So we'll know that. And it's dependent upon the concentration and the temperature, independent about concentration and temperature. Concentration and temperature can help you get over the hill quicker, but they don't adjust it. The only one that lowers the hill is the catalyst. The catalyst actually lowers the actual activation energy. So it's the same at the beginning as it was, same at the end as it was in the beginning. So then we talked about this. We saw that this is a endothermic reaction, and this is a exothermic reaction. So again, this one is endo. We have a high activation energy. This is exo. It has a lower activation energy. Therefore, the endo is slow, and the exo is fast. And this needs a lot of energy, where this one needs very little energy to get over the hill. So you need to get over the hill. Now, introduce another term, activated complex. At the very, very top of the hill, it has the highest energy, is a very high energy, therefore it is unstable. So that's our activated complex. Activated complex is also called the transition state, because in this situation, the oxygen is actually being transitioned between the two. It is very unstable and is at a high energy. Make sure you do know that. Very unstable, high energy. Moving on, then we talk about temperature. We just know this. You increase the temperature, you increase the rate of the chemical reaction. Temperature, you increase the temp, you're going to increase the kinetic energy. Okay, they're going to be moving faster. That's all we talk about. We plotted it out here in this graph, but that's really the only thing you have to really pay attention to. You increase the average kinetic energy, more of them are going to exceed the activation energy then, because they have a higher kinetic energy. We talk about these three, make sure you know them. These three aspects can increase the rate of a chemical reaction. In this situation, particle size and concentration are just going over the fact of collisions. You're just increasing collision, not going after geometry nor kinetic energy, just going straight after increasing the number of collisions. More collisions, more successful, greater opportunity to be successful. Kinetic energy goes after, or temperature goes after kinetic energy, and catalyst goes after, is kind of a roundabout dealing with kinetic energy because it lowers the activation energy. It's the only one of the four there that actually lowers the activation energy. This plot right here, just a great example that my Reactants start up here and products start at 0, and that's where we always start. We got the ice, we always have 0 product. So a great example, and we reach a point of equilibrium there, so that we plotted that out with our lab. Then we went on this. This is not going to show up on the test. The only thing that's going to show up on the test will be this, if we add the exponents up. So what I mean by that, I'm not doing any math for this on the test. All I mean is this. So if I gave you a problem, I said, well, let me get to the second example here. Let me move on through this, because this is not going to show up on the test. Don't panic. It's not going to show up. You don't have to worry about it in the whole process. So as I go through this, no, you don't even have to worry about the units. It's not going to come into play. Well, let me show you what I talk about. So in this situation, I would say this. I would say we do the first one. You say, well, this first one is the exponent is 1, therefore it is a first order reaction. Then my second reactant in this situation was y equals 0, so it's a 0 order. Overall, it is a first order reaction. That's all I would do. That's it. One is, if I have a first order and I have a second order, what's the overall order? You would say overall order is the third order reaction. That's all you're going to see on the test. Don't worry about any of the math. Don't worry about any of this stuff. So let's go on. Let me get through this. Moving on. We now move to reaction mechanism. Don't worry about any of this. Nothing's coming up. Nothing's coming up. Here we go. Here's the key thing. Know it, know it, know it, know it. The slowest step in a reaction mechanism is called the rate determining step. The rate determining step. Make sure you know it. That's it. Moving on. We're going through this really quick. Don't we know anything about the ozone. But again, we did speed up the process of breakdown. Reversible reactions. There we go. Understand reversible reactions. First of all, when we say rate, equilibrium has nothing to do with the amount. It's the rates that are equal here. Just like Kinetics studies the actual rate itself, equilibrium, or the rate going forward and the rate going reverse are the same. Don't worry about anything here. And we got to these 3 stresses. Know your 3 stresses. Know them, know them, know them, know them. And they go into the Charlotte principle. So let's go to the Charlotte principle. First of all, understand, if I give you energy, I don't have to tell you exothermic. What if I put the energy over here? You're going to say, oh, then it's endothermic. Okay, so in this situation, just which way does the car roll when you again, in this situation. So in this scenario, it is an exothermic reaction. I'm going to raise the temperature. That means I'm going to increase temperature. Therefore, the car is going to roll to the left. Does everyone follow that? Straight up, pretty easy. Now, what must happen to reach a new equilibrium? My reactants must increase and the products must decrease to reach a new equilibrium in that process. Make sure you do understand all that, but that was temperature. Pressure only deals with one state of matter, and that state of matter is gases. And all I'm adding are coefficients, and my gases move from where there's more, 2, to where there is less, 1. And so it's a 2-to-1 ratio based upon the coefficients. So again, from where there's more gases to where there's less, when I relieve pressure, it goes back to the larger number. So it would move back towards a 2 in this situation like this. Moving on, concentration. Concentration now is the only one that I specifically call out someone. So I said ammonia. You say here, where I add ammonia, that means I do that, and that means the reaction is going to shift to the right. And when I add water over here, that means the reaction is going to shift to the left. So that's, understand that issue. Understand this. We went through some biochem. I'm not going to do any biochem on you. So go through all this, fly through all this information, so I can delete all this stuff. But here we go. This is going to be on the test. This is going to be on the test right here. Don't worry, I'm not going to do this. I'm not going to bring this up. The fact is this, it's the products divided by your reactants. The products divided by your reactants. A couple things you must know. First of all, there are no units. Again, the concentrations I'm giving you back there are at equilibrium. They're at the E in your ice. We don't use solids or liquids, do not show up in the expression. If it's greater than 1, the products are favored. If KEQ is less than 1, the reactions are favored. You better know that. You better know that. Be aware of that. Be able to recall that aspect of it. Moving on. We then wrote out, we did some practice here, just actually writing out the equilibrium expression is the products over the reactants raised to the power of their coefficient. That's all it is. If it makes you feel better to put parentheses around them, feel free to put parentheses. If the brackets confuse you, just put parentheses. But that's our equilibrium expression. So then we moved on to this example. We're going to go through this example. So basically what comes up here is I have reactant, I have no product. So remember this. Let me go back here really quick. So I have water in my A, but I had no water in B, correct? So we have 0 product. then a change occurs. You realize when you start transferring your water, the A decreases and your B increases. So I represent that by subtracting my change, and then over here I'm adding my change. And then I tell you that at equilibrium, at E equilibrium, C had the value of 0.160. Now remember, like I told you in this situation, basically you're doing simple arithmetic. I'm adding here, and I'm subtracting there. But I had to figure out the value of x. So I know this. 0 plus something gave me 0.160. Therefore, x has a value of 0.160. And then I plug my x's back, plug that value in back across. And here I subtract and get my answer. So I get these answers. Now I can plug them into my expression, which is the concentration of the products divided by the concentration of reactant raised to the power of its coefficient. There we go. And then we just plug these numbers in and do the math. Easy. Next one, this I love to show on the test because I don't give you molarity. This one I gave you, this one back here I gave you molarity right off the bat. This one I don't give you molarity off the bat. I have you work, I give you moles, but molarity is moles per liter. So look for the liter of the tank. Now in this situation it happened to be 1, therefore it ends up being numerically the same. I kept it easy for you there. And then we run through ice. Again, initially I have my reactants, I have no product, my reactants decrease and products increases. But again, I have a 2 here, so it increases by a 2x. That process. I also didn't know that equilibrium here, so I go 0.100 minus something equals 0.080. Therefore, I realize that x equals 0.020, and I plug that back in. 0.020, 0.020, and I have 2 of them, so 0.040. And then I do simple math. So 0 plus 0.040 is that, and then this one ends up being the same. So I get all my answers. Once I get my answers for E, those are the values I plug into my equilibrium expression. So what was my equilibrium expression? It was the concentration of my product raised to the power of its coefficient divided by the concentration of my reactants, both raised to the power of 1. So I plug that in and I square it. Now these were 0.080 times 0.080, but I just shortened it up and squared it, correct? So that's all it is. And then we solve. There you go. There's your test. Good luck. We'll see you guys tomorrow.